Milisavljevic, okay, thank you. So he's a professor in Purdue University, right? Enhancing ZTF public survey for science inferencing with REFIT. He's going to talk about that. By the way, you can join the channels in Slack for each one of the sessions and post questions and answers there for the speakers also to monitor whatever your session, your talk is, and also so the discussion can continue if we run out of time here.
Okay, I guess I'll get started. Armin's a tough act to follow, especially with all that exciting news. Thank you for the organizers for having me here. I'm seeing a lot of people in person and virtually. The kind of experts I really want to be interacting with the project that I'll be discussing here today. I'm here by myself along with grad students Bugya and Danielle in the back. I hope you get to meet them. But also I want to highlight the legion of supernova superheroes that I work with on a regular basis. You know, they're called into action at certain times. And of course, if audio was working, you'd hear the choo-choo of the Purdue locomotive there. That's a team that I'm working with. I'm sure many of you were asked, have you seen the movie Don't Look Up as astronomers recently? We take a different approach. We want people to actually look up, and that's a group photo here. Okay. This is a slide where it's bottom line up front. The overall goal of our mission with the recommender engine for intelligent transient tracking, which you'll hear me abbreviate as REFIT, is to enhance public all-sky data and to do it in a way that makes it as simple as possible. Remember, KISS, keep it simple, stupid, right? To try and avoid, for certain science cases, to try and avoid complex lists of objects and cherry picking, and have a very simple interface where if you have spare time at a telescope, you know precisely, you're guided to an opportunity that provides information-rich data to some scientific objective. Okay? And we are creating a crowdsourcing platform to make that possible. So users are quickly guided to science-rich targets. They're coordinated amongst each other, and it provides an easy way to submit the observations. And anybody that's done this in some capacity realizes every step along the way is complex. So we have our eye on LSST, but we've been working with the ZTF public survey stream as a test case. Now, the ZTF actually has a cadence that's pretty good for supernova science, and here I'm highlighting light curves presented in the Dan Perley paper. But these have kind of been cherry-picked for the nicest ones. There's a lot of ones that aren't so nice, and this is from the BTS survey, so that's things brighter than 18.5. Once you start going fainter, right, and you want to push the limits of your abilities, where a lot of the supernova light curves are actually going to live because you're going further into the universe, things don't get as clean. And even with the ZTF stream, it's 2 bands. Okay? We don't get privy access to the I band. So there's opportunities to augment, to add to these light curves. And again, start thinking differently from as a discovery machine purely, okay, where it's something discovered, then you coordinate your facilities to densely sample that light curve as much as possible. You want to be actively augmenting in a smart way so that you make most efficient use of limited resources. So instead of ... you only cherry pick the most important epochs that provide most information for you. Okay? That's ZTF. This is what I'm going to discuss most. Of course, LSST isn't as beautiful. Here is what a type 2 supernova will look like in the first 30 days since trigger, okay, in the WFTD field. This highlights the kind of necessity for what we're trying to achieve. So we're instead of sitting back and after the fact trying to make a classification about this, let's actively augment in ways so we can make it possible to extract physical parameters, things like kinetic energy, ejecta mass, progenitor radius, nickel-56 yield. Right? It's questionable how much we'll be able to extract that out of the majority of supernovae that LSST will find. Okay, we often advertise, you know, in the first year, LST will be able to find, you know, 100,000 more plus supernovae. A lot of those are going to be junky light curves, right, that we can do limited science with. So let's actively augment in ways to increase the science value. Okay, and my thinking of this comes from helping amateurs contribute to supernova science, and Purdue has been helping to support the work of David Bishop. By day, he's a software engineer, but every night for a couple hours, he maintains this bright supernova webpage, and he has for decades, cataloging all publicly announced supernovae. Now, 10 years ago, this list was actually manageable. You know, a couple hundred supernovae per year. You could scroll through, oh, I like this one, I like that one. It's a great resource for finding charts as well. But now, in recent years, where tens of thousands of supernovae are being discovered every year, you know, it's much more challenging, and you have lists and lists of objects that are complicated. Okay? I wanted kind of like a Netflix recommender service. For anybody who has some spare observing time, hey, what should I look at now? And now often people will email and etc. But that's not maximal, I mean, that's not efficient use of limited resources. Okay? Let's coordinate it in a simpler way. Okay? We want to avoid bunch ball. So if any of you have kids and you watch them play soccer, they'll all go to the soccer ball, right? Supernova people can tend to do the same thing, where there's a flashy new thing and they jump after it, okay? Or they chase after it and they get distracted and they go from one thing, as opposed to having a coordinated field. Okay, so everybody here, and the talks in the next couple of days will emphasize this just by reading over the abstract, is that it can't be business as usual as we move into the era of LSST. Okay? It needs some kind of decision support system that updates from beyond manually operated data collection with some fully automated approach that can make reliable, time-sensitive, on-the-fly decisions to adapt and maximize return on well-defined scientific objectives. And I'll try to discuss a little bit more what we mean by scientific objectives in a moment. Okay? So our approach that we initiated a few years ago at Purdue is this REFIT system. And we designed it to be, and we named this thing called an Oracle, Object Recommender for Augmentation and Coordinating Liaison Engine. In essence, it's a souped-up Tom or Marshall, in the sense of going beyond lists of objects and watch lists and coordinating with observatories to just singling in, providing marching orders between observatories to maximize science opportunities. And the system takes into consideration the diverse telescopes and instruments that are available, weighted by the respective costs and benefits, you know, doing all this in an automated sense. So here's a flow chart of what we're trying to do. At the one level, I guess I'll use my, no, I won't do that, I'll do this. We have some stream of information. Okay, right now we're tapped into Antares, where we have a live streaming service that's connected originally to the ZTF, of course. And then this goes into the REFIT system. The REFIT system then looks at all the events, okay, and the light curves of them, and makes some kind of predictions, forecasts. How will that light curve evolve? Now, this is a whole module that I won't get into. Ari will have a talk tomorrow talking about her system that she originally wrote and developments from that. Bhagya will talk about, and that system, by the way, is data-driven. So we use templates of previous examples to guide us on how things are going to evolve in the center. We're also trying to move towards science-driven forecasting and recommendations. So instead of preview events, we use simulations. Okay? And simulations have the benefit that they come along with physical parameters, explosion energies, nickel masses. So you can be guided by those parameters as opposed to just likeness to previous events. Okay? Anyway, it makes forecasts, and then all of a sudden it makes recommendations. And those recommendations are broadcasted to users. Okay? Those users hopefully act on them. They make observations. Those are reported back into the REFIT system, which ingests them, incorporates them in the next round of forecasting, and the loop continues. Okay. So our REFIT is this crowdsourcing platform, is hopefully streamlining the decision making. So any user have available time. You know, which target is the best to observe right now? And best is italicized because that's really dependent on your science objectives. The next is the data processing. So the sharing of the data, getting it in, and ensuring uniform calibration. All major things to take into consideration. Okay. Here's what it looks like. Here's a screenshot that I took from yesterday. Okay? You can see, oh, by the way, you'll immediately notice that we have an auto name generator, just because it's hard to remember, ZTF 22AATEMPQX. People, when you type it in, that's also confusing. So sad-friendly Stern, and it's adjective, and famous scientist last name. I looked it up. Lena Stern was a Russian biochemist. All right, here's the light curve coming in, and I can highlight this. Here is the forecast. So you may wonder, hey, you're not doing your math well here. You're not following the data. This is based on prior events. So in the templates, this is the best fit that we could find of events that that it's been trained on. And here's the recommendation. It anticipates that the supernova will hit that. So that provides a magnitude value that can be matched appropriately to aperture size of the telescopes in the network. Now it doesn't know it for sure, so it asks, hey user, please obtain an observation around this time frame in the R band. Yeah, that's what I want to say. So what do we mean by scientific objectives? How do you choose which targets are the ones that you want to go after and which epochs? Right now, because it's a crowdsourcing platform primarily with amateurs, it's the very simple objective, kind of brainless but yet important, for objects that are nearing peak. Okay? Constraining the peak can provide information about nickel mass, among others. It's also the brightest time of the supernova, and that helps for amateurs with have a smaller aperture size. However, we have other ways of gauging scientific objective. Classification. Perhaps there's certain classes of supernovae that you want to be recommended. Okay? Type 1As, core collapse, etc. Anomaly. A lot of people will talk about that. So which objects are most disparate compared to your training set? And then other, error in forecasting. This is what the original REFIT design was for, was how much uncertainty is there in constraining where the light curve is going. So here's an example of REFIT in action. The shaded blue region is what has been observed. Okay? This is coming afterwards, but this is what's been inputted into the system at some time frame. You see only 2 points. REFIT makes this forecast. Okay, you see the large region of uncertainty in this best fit. This is subsequent data. But even with these two data sets, two measurements, you can see it made some reasonable estimate about where it's going. This triggered an observation at this point with the MDM 1.3 meter, which thankfully was saved from that devastating fire that worked its way through Kip Peak. And here we're able to constrain the peak a little bit better in light of having an observation. Okay? Now, you could say, you didn't really need that, Dan. ZTF is fine enough, and I could have constrained it. But this is baby steps, just moving forward to this eventual goal of actively augmenting a data set. Okay? As I said, ZTF has a cadence that's pretty good for supernova observations, although it can have complications. Okay, and then here I highlight real quickly another coordinated observation. This was provided by Stu Parker in New Zealand on his 0.3 meter. I also want to highlight Danielle made the color transformation to go from unfiltered into an R band. This is a great scenario where we can coordinate observers to extend a light curve. So if this is a southern hemisphere object, somewhere along the equator or lower, ZTF won't continue it up until some point, at which point you could pass it on to the southern observers and extend the light curves. This is very helpful, for instance, like type 2Ps, which have this long thing, and you want to catch that drop at the plateau region. Okay. I see I got a 5-minute mark, so I'm not going to go into detail. This is the flow chart describing how the original REFIT system that was published in Ari's paper in 2020. The ZTF system has been trained on ZTF BTS objects, Pan-STAR objects, and any historic classified supernovae for which there is sufficient photometry that we could get into SDSS to match with the ZTF. Okay? I'm going to pass on that just to be interest of time. I'm also going to pass quickly, because Abagi is going to talk about this in her talk, emphasizing that there are opportunities for science-driven decisions. So here is a type 2 light curve. You can see the points coming in. Here is the drop-off region. Hopefully, we can have REFIT making recommendations in this information-rich epoch, right? This is when it anticipates a drop. So if ZTF is weathered out at this point, or if it's going to drop below the horizon, we want to prioritize an observation here. Now, by eye, it looks at, hey, I know I want to observe that, but when you have thousands, tens of thousands of objects to select through, you want an automated service to make sure it comes to your attention. Okay? I also want to, okay, I'll skip over this. This is all the architecture. I'll shout out to Jeff Lettner, who is our computer architect. If you ever seen the second Matrix, when he goes to the art, that's really him. He takes control. These are all the physical assets, computer systems that speak with one another to make this all happen. This is the observer network, in part, that is part of REFIT. It spans hemispheres, and I wish I could talk about Greg Bach. This is a bar by day, and then by night it opens up to open up his telescope for observing. I've also put some skin into game. I purchased an 11-inch Celestron telescope. Here, Andy, please look at this. So here's a great emphasis of how, in my backyard, in downtown Lafayette, Indiana, I can still get observations that contribute science. So here I'm comparing it to an LCO GT 0.4 meter, which we got, thanks to them, there was a AAS workshop, and you gave out in a lottery system some time, so we were able to use this. So as happens, you have tracking errors, right? More eyes in the sky mean more opportunities to observe transients, and here you can see that I was able to get that. I'll just go there. A couple nights later, LCO, clouded out. Next night with the downtown Lafayette Observatory, I was able to still observe it. The technology is improving so much that somebody in their backyard with a cold beverage that I won't speak of can still contribute science-worthy things. And you think, oh, these are too faint for LSST. Yes, but by using smaller aperture telescopes to chase after fainter targets, that relieves larger aperture telescopes to go after the targets that they should be. Okay? Yeah, I'm just showing, I don't even have a great system because I can't polar align my telescope because trees are in the way. I also, yeah, okay, I'll just go on there. In questions, perhaps I can talk about that. I want to go over one thing. So I'm highlighting examples. Oh, yeah. The zeolite particles, everybody remember that contaminated the ZTF camera for like weeks at a time? So we're able to augment inside that region. And then final thing, because I want to be respectful of time. So we're making some progress. Our attempts for spectroscopy, you can maybe ask for that afterwards, but this is what I wanted to make sure. In our experience, now we are connected live, as it were, to the Antares stream. But in our experience dealing with data brokers, we're finding that brokers aren't all reporting the same photometry. And you would think so because they all get the same fire hose, right? So I've seen these plots a lot, but let me explain it to you. This is a light curve, the red points, the green points. Wherever you see a circle, it means a broker hasn't reported the same photometry. What you do is you use whatever broker returns the most, because we don't have access to the ZTF directly. Often it's a Lersey that reports with very, very minimal signal-to-noise cuts. But you can see here in Fink, there's this whole region of rising in the light curve that's not being reported in the photometry. We have some purple, these circles here are associated with Mars data. Yeah? And this is just grabbed from the other day. You can see this rise. You see circles everywhere. Okay? So a Lersey has reported all these values, but these other brokers haven't. Now, this isn't lower signal to noise, I know, but that's not always the case. Okay? When I spoke to a Lersey representative, they're somewhat aware of this, and they think it could be a Kafka issue, which is to say, sometimes a stream comes in so quickly that events are dropped. Okay? So they aren't retaining all that information. And if this is happening in the era of ZTF, it's frightening to think about what's going to happen in the era of LSST. Okay? I have this plot, but I'm going to just, that explains it more. This is the number of data points that's disparate between data brokers using the one that reports the most as a benchmark. And you can see that we can miss hundreds or thousands of data points at a given time since peak. Okay, I'm going to leave it at that. Thanks very much for your time. I hope I've spurred on some interest. I look forward to speaking with everybody here. So long.
Thank you, Dan. Questions in the room? Yes.
Hey, I had a question about your italicized best. in the way you define
yes?
Yeah, what REFIT thinks is best. Because if I want to optimize a science case, is it easy for me to tell it, oh, I want to like catch things during peak to find nickel mass, or do you want to like get late time observations to look at bumps? Like, I really see how REFIT's recommendations would really depend on what I want to do. So is it easy for someone using it to change that?
Right. So right now, REFIT operates on just this peak since light curve. In the next phase, which hopefully happens in the next 3 to 6 months, there will be other priorities made available to them, the ones that I talked about, supernova type, late time evolution, maybe science review. But at the very end of the day, in our platform, one has a slider, percentages. How much of your time do you want on this scientific objective versus another, right? And my hope actually is that the community will adopt something like this in the future. I actually pitched this for the ELT Key Science program for transients, where a community, similar to a TAC, comes together and agrees upon, we're going to spend this much time on type 1As and this much time on superluminous supernova, however the science is, and then you have a recommender engine that just targets these objects according to those percentages that have been allocated by the community, and all that is public.
So, supernovae are often on galaxies, and if you're an amateur or something, you don't have the subtracted image. So how do you deal with that? And then the fact that amateurs sometimes you'll have different levels of calibration, and some people's may be better than others, and so if you get a bad point, it might throw off your prediction.
So sharing of good and bad. So here is photometry. I wish I had an image of the galaxy here, but here's photometry. That's a relatively bright. Let me go to a fainter object here, a little bit fainter. So here's an this is a great example. So here's an example where this is kind of pushing the limits of a 12.5-inch telescope located in a remote site in California, what it can do. And we've been using, in this case, Cinnamon provides the data to us, and then we use template images from ZTF to do the subtraction with hot pans. And this is slowly improving with time. So that's why we gain value in them providing the data directly with us. And then from that, we can do calibrations right on field differential photometry. But that is a service. It depends on the user having appropriate filters. And in this case, it has the appropriate Sloan filters to do so.
Hi, really wonderful talk. I was wondering if you could talk a little bit about your thinking for anomaly detection, especially since it seems like a reference library of simulations based on probably things that we've already seen seem like they're key to the current infrastructure.
I'm going to defer that to Bhagya in the interest of time. She's going to address that directly about how we can use these scientific priorities to direct and find anomalies that are outsiders. Yes?
Thank you.
Thank you.
Thank you again, the speaker.